Hello, good morning, everyone. So, as I told you, today we'll be starting with Coulomb's law, right? And what we'll be doing in Coulomb's law is that we will be talking about forces between two charges. We know that like charges repel each other, right? And unlike charges attract each other. We know that already. So, what we're going to do today is that we're going to develop relation between the or we're going to find the force relation between the two charges. So till now we know that force acts, repulsive force acts and attractive force act. We know forces act, but we do not know how much, right? How much force acts. So that how much value, the amount of force, the magnitude of force is given by Coulomb's law. Magnitude and direction of force is given by Coulomb's law. And that's what we're going to study here, right? So let us say you have got two charges. Let's say this is Q and this is also Q, and they are positive charges. So between them there will be attraction or repulsion. There will be repulsion, right? So this charge will feel a repulsive force in this direction called F, and this charge will also feel a repulsive force in this direction F, right? And where the forces in this direction, right, away. And what will be the forces here? It will be attractive. So this object will will feel a force of attraction. In which direction? Towards the negative charge, right? So one F here, and this negative charge will also feel a attractive force because of this positive charge. And where will be that direction? Left or right? Of course, it will be towards left. Yeah. So we are saying the direction of force is either in this direction or in this direction. No matter how it is along one line. Can you notice which line is that? It is this line. The forces are along this line. Can everyone agree? These are two different cases. But the forces are along this line. And what is this line, guys? This is what? It's a line. It's a line joining the two charges. Here also, it is a line joining the two charges, right? So what can I write? Forces are along what? Along what? Along the line joining the two charged particles, right? So forces will always be along that, guys. Along what? Along the line joining the two charged particles, right? So the magnitude. So this is the direction part. Then we'll go into the magnitude part. So first we take down the direction, and then I'll tell you the. In the next slide, I'll tell you the magnitude. Now let us talk about the magnitude of the charge of the force. So we right now saw the direction, and now we are going to talk about the magnitude. Right? So force between the two charges magnitude is given by the form is proportional to magnitude of q1 magnitude of q2 divided by r square. Now what is r here? As you can see, r is the distance between the two charges, and the force is found to be proportional to the charge magnitudes divided by distance square. And since the force magnitude is proportional, there will be a constant of proportionality which is called Coulomb's constant, which is represented as K. And the magnitude of force becomes K times mod Q1 mod Q2 divided by R square. And there is a constant of proportionality called K, right? The value of K is given by this equation, 1 divided by 4 pi epsilon naught, where pi, as you know, is 3.14, right? But this epsilon naught fellow, its value is a weird value which you have not seen before. It is around 8.85 into 10 to the minus 12 coulomb per Newton meter square. And what is this epsilon naught called? It's called the permittivity of free space or vacuum, also called, you read it as epsilon naught, and it is called permittivity of free space or permittivity of vacuum. That is, this is the value of epsilon naught, and the value of K is quite simple. It is 9 into 10 to the power 9 Newton meter square by Coulomb square. So what is the force proportional to? The force magnitude is proportional to the magnitude is proportional to the product of the magnitude of two charges. So we can write force is proportional to product of magnitude of two charges, and inversely proportional to what? To the distance. And is it really distance? No, square of distance. So inversely proportional to the square of distance between charges. And then we have an extra point here which says, does the Coulomb law follows Newton's third law? The answer is yes. Coulomb's law also follows the Newton third law. So what do we mean by Newton third law here? As you can see, this is the force on the positive charge. By whom? Force by negative charge. So negative charge applied a force on the positive charge in this direction. And Newton third law says that every force has got an equal magnitude and opposite reaction. So if this force is there, opposite of this force will be this force, right? So you see, of equal magnitude, magnitude is also equal, it is same F, but in the opposite directions, right? And this force is on negative by positive, whereas this one was force on positive by negative. right? So do they follow Newton's third law or not? Yes, because you see this is the force on positive by positive, and this is also the force on positive by positive, same force but acting in opposite direction, equal magnitude but opposite direction. So it follows Newton's third law. So does the Coulomb's law follows Newton's third law? The answer is yes, right? So write down this. Now let us see relative permittivity. So what is relative permittivity? It's also called dielectric constant or relative permittivity. It is represented by epsilon r or epsilon rm or k, right? But k will not be using, will be using this, right? Will not be even using this. But all these are also notations. But currently, I'll be using epsilon rm. Dielectric constant or relative permittivity expressed by k or epsilon r or epsilon rm. It is a ratio of permittivities. Ratio of permittivity of a medium to the permittivity of free space. So epsilon Rm is the ratio, as I said, it's a ratio of what? Epsilon m. What is epsilon m? Permittivity of medium. Divided by epsilon naught. What is this? We have seen this before in the last section. What is epsilon naught? Permittivity of free space. And when you divide the two permittivities, what you get is called epsilon Rm, which is called relative permittivity. Here, what is epsilon m? It's the permittivity of the medium. And epsilon Rm value is always greater than or equal to, can you guess? It is always greater than which value? Always greater than 1. So can I say that epsilon Rm is a dimensionless and unitless quantity? Is it true or false? Is epsilon Rm, which is the relative permittivity, is it a dimensionless and a unitless quantity? What do you think? See, it is permittivity of medium divided by permittivity of free space. So basically, you're dividing permittivities only, right? This is permittivity of the medium. This is permittivity of the free space. But after all, both are what? They both are permittivities, right? So when you divide permittivities, one permittivity upon other permittivity values will get cancelled, the units will get cancelled, and there will be no unit left. So yes, it is unitless, and since there is no unit, it is also dimensionless. So it is true that it is a dimensionless and unitless quantity. Now, what will be the relative permittivity of vacuum? Think about it. What will be the relative permittivity of vacuum? And what is the permittivity of vacuum? Permittivity of vacuum, I told you, like I have been telling you, what is epsilon naught here? Epsilon naught is permittivity of, sorry, epsilon naught is permittivity of free space. Free space means what, guys? Vacuum. So what is the permittivity of vacuum? Epsilon naught. That we've already seen. My question is, what will be epsilon r, or more like epsilon Rm of vacuum, which is also called relative permittivity of vacuum, I'm asking you. So think about that, and while you're thinking, you can copy this stuff. Take it down, and also think about this question. You have to answer this question yourself. Think about it. Once you have copied down, I'll tell you, and we'll move to the next slide.
doubts, please raise hands. You can ask me if you have any doubt. In epsilon r of vacuum, epsilon r m of vacuum, what will be that? Epsilon r m, let's find out.
We'll do it on the next page. Here we'll find out. So epsilon Rm of vacuum, that will be epsilon m divided by epsilon naught as per the formula, as you can see here. See, epsilon m divided by epsilon naught. And what is epsilon m? It's the permittivity of the medium. Divided by permittivity of vacuum. But here we have to find out the permittivity of which medium. What is the medium here? The medium that we're talking about is vacuum only, right? I want to find the permittivity of vacuum. So when you say permittivity of medium, so I can write epsilon Rm instead of m. What is the medium here? Vacuum. I can write epsilon Rv also, right? So what is epsilon Rv? Well, this is the a vacuum, right? Relative permittivity of vacuum. And that is coming out to be equal to what? Permittivity of medium. And which medium are we talking about? Which medium's relative permittivity you have to find out? Vacuum itself, right? So that medium itself will become what? Vacuum. So basically I'm saying in the numerator I have to put permittivity of vacuum, which is epsilon naught, divided by permittivity of vacuum, which is also epsilon naught, giving us 1. So what do we get? Epsilon Rv is coming out to be what? 1, which is the relative permittivity of vacuum is coming out to be equal to 1. Now let us say two charges Q1 and Q2 are kept r distance apart in vacuum, and I want to find the force between them. So we already know the force between them. What is the force between them? It is 1 divided by 4 pi epsilon naught Q1 Q2 magnitude divided by r square. That's the force, right? Now if I want to find the force when it is not vacuum, means any medium. Let's say it is any given medium in that case. If it is any given medium, then what is the force? You know, it is given by 1 divided by 4 pi epsilon naught. But since it is some medium, so that medium's epsilon r m also comes here. This term also comes here, and this term depends on nature of the medium. Into mod q1 mod q2 divided by r square. So this force and this force are same, almost same, except one term, and that term depends on the nature of the medium. So if these charges are kept in, let's say, inside water, these two q1 q2 are kept inside water, then the term that will come here, epsilon rm, will be the epsilon rm of water, right? And epsilon rm of water is how much, you know? Water is 81 and free space is 1, right? So likewise every different medium have their own values of epsilon rm. So I can say that electrostatic force is medium dependent on or independent. It is medium dependent. And how does it depend? This is a term that forces it to depend on the medium, epsilon rm. Everything else is same. Right now? So let's go ahead and talk about conservative forces. So what are conservative forces? Let's see that. Work done by conservative force, CF is conservative force. Work done by conservative force in any and every closed loop is equal to 0. That is what is a conservative force. That work done by such a force in any closed loop will be 0. What does that mean? That means that if I start from this point, if I go all the way round and round and round and round, why I'm saying round in this, because I'm coming back to the initial point. So I'm forming something called loop. Loop means what? Starting and ending points are same. And I'm coming back for I'm forming a loop. If the work done by such a force is 0, then that force is called conservative force. So write down what is conservative force. Also, work done by such a force means which force? CA, conservative force. Work done by conservative force is path dependent or independent? Is path independent. What does it mean? Is that, let us say you go from this point to this point, taking path number 1, and the work done by the forces, let's say W1. But your friend, let's say your friend takes a different path. path number 2. And work done by the force in this case is, let's say, W2. So work done by that force in the first path is W1, work done by the force in the second path is W2. If the force is conservative, W1 will become equal to W2. So that's what I'm saying, that it does. So does it depend on what path are you taking? It doesn't depend, because no matter what path you take, let's say you take a different path, call it path number 3, and work done by the forces, let's say W3. So this will also be equal to what? W3. So that's my point. My point is, no matter what path you take, as long as the force is conservative, condition is conservative, it should be conservative, right? As long as it is conservative, work done by those forces will all be equal. W1 will be equal to W2 will be equal to W3, right? So I can say that work done by such a force is path independent, doesn't depend on path, and also it is, all the works are also equal, and equal in all possible paths. Then it only depends on what then? Then work done only depends on what is your starting point and what is your ending point. So it only depends upon start and, or initial and final points. That's what it depends on. Work done only depends on initial and final point, because if you change the initial and final point, let's say you take a different initial and final point, then work will be different, right? Then it is not guaranteed to be same as that of other works. Like, let's say you say, no, I'm not taking this path, I'm taking a different path, and also my final point is also different. This is my final point and this is my initial point. Then what will happen? Let's say the work done here is W4. Then W4 will not be necessarily equal to W1. W1 will be equal to W2 will be equal to W3, but they will not necessarily be equal to W4. There is no guarantee that they are equal to W4 also. It might not be equal also, right? So that is why it depends only on initial and final points. As long as initial and final points are same, like for path 1, path 2, path 3, initial points and final points are same. So as long as initial point and final points are same, the work done will be same. But if you change initial point and final point, then the work done might be different, right? That is not guaranteed. Take this down. So let's go ahead now. And this is a lot of math to decide if a force is conservative or not. You don't need it as of now. Okay, now let us see what is the central force. So a central force on an object is a force that is directed towards the center, towards or away from a point called the center of the force. So let's say that there is a point here q1 and there is a point here q2, right? So let's say the force on q2 will be in which direction? It will be along the line joining the two charges. So let us say it is towards q1, let's say, and then your q2 moves from here and comes here. Now where will be the force on q2? In which direction? It will be again towards q1, right? Here also it was towards q1. Here also it is towards q1. Then q2 moves further, let's say. It goes further and let's say reaches here, q2. Then also force will be towards q1, right? So you are seeing that force is always towards one point, and that point is called center of force. That point is called center of force, because force is always directed towards one single point. That's called center of force. And such a force is called what? Such a force is called central force. Means a force which is always directed towards a point is called central force. So is Coulombic force central force? Yes. As you can see, it is always, the force is always directed towards a point. Now it could also be directed away from point. Let us say if there was repulsion. In case of repulsion, the force between them will be what? It will be away. Here also it will be away, and here also it will be away. So here, but in all the three cases, we see that they are away from one point, which is called the center of force, right? So that is why it is said that either the forces are towards or they are away from a point called center of force. This point is called center of force. The forces can either be towards that point or away from that point. Towards that point, away from the point. Towards that point or away from the point. From a single point, that point is called center of force. Such a force is called central force. So out of this example and this example, can you tell me which one is the central force? So here if you see, the force is acting here and it is not towards a point. Right? The point is here, but the force is here. So this is not central force. Whereas here, it is away from a point. So this is a CL, means central force. Got it? So take this down, and that's all for today.